In the last class, we went through kinetic theory of gases, and by now you must be having the understanding what causes the pressure, right? What causes pressure in a container? How do gases exert pressure? So, can anyone say like how gases exert pressure in simple terms? I don't want you to go to the equations, but just like how do gases exert pressure? Simple, yeah.
Particles start moving faster and spread out further. So if they're in a fixed container, they have more collisions with the walls.
Yeah. So how does it cause pressure? Like I want you to kind of come to that point.
The increased amount of collisions, right?
Yeah. How do the collisions create the pressure? That's where I'm.
Collisions exert force.
That's where you should. So collisions. For each collision, there's a change of momentum, and rate of change of momentum is force. And when these forces are happening on a certain area, then force over area gives the pressure. That's how you should answer it. Okay, so microscopically, that's what it is. Atoms are moving, fast, random directions, random speeds, but finally they bounce, undergo change of momentum, therefore a force exerted, and the force exerted per area gives you pressure. Get it? So that's how pressure is created in any container. Now, what we are trying to do today is first see how that pressure is connected to the other factors, which are volume, temperature, okay, and other factors. So let's see what are the factors that pressure depends on. Okay, so that's where you have these laws coming in. So the first of those laws is Boyle's law. Boyle's law is trying to connect pressure and volume. Pressure and volume. And how we can easily explain Boyle's law is consider what does it look like?
Piston.
A piston and a cylinder. Okay, so there is some gas inside here, and I can connect this piston, this cylinder, to a pressure gauge. I can connect it to a pressure gauge, so that will indicate the pressure inside. Okay, so at some position of this piston, if there is a pressure created here, call it P1. The pressure that is recorded here is because of the activity of these molecules and how they are colliding with the walls of the container and so on. Now, what will happen if I move this piston from there all the way to here? If I move the piston from there to here, halfway down the line. So what will happen? What will happen to this trapped air there?
That's half the volume.
It's half the volume, but how does the pressure increase? Can you explain microscopically why the pressure increases? In the same terms as you explained the previous thing, can you explain why is the pressure increasing here? Yes?
The molecules are moving at the same, like exerting the same force, but they're much more condensed.
Yeah, that's right. Because now you have smaller, you reduce the area altogether, you reduce the volume. So when you reduce the volume, what happens is on each wall, the collisions are taking place more often. So for example, after bouncing here, it'll go here and come back and bounce again, right? The time between collisions. Now what happened to the time between collisions when you reduce the distance? It's also reduced. So when the time between collisions is reduced, it's going to have more collisions often. You understand that?
Yeah.
So between two walls, like if it was going before from hit, like that, what will happen when you reduce the gap here, hit, it's taking shorter time to kind of come back again and hit again. So therefore, the number of collisions is going to increase. And therefore, the overall force increases, therefore the pressure increases. Do you get it? So when you reduce the volume, the pressure is supposed to go up. And so that's the volume I'll call it V2, and the other one is the volume V1. If I'm considering the area to be the same, so the volume is basically proportional to the length of the piston also. So this is something that you can do. You just take a syringe, a simple syringe. Now keep the piston at some position, connect it to a gauge, move the piston, and change the length, and you can actually see how the pressure changes. It will be perfectly varying. So what kind of relationship is this? Pressure and volume, how do they actually change? Pressure is inversely proportional to the volume. Pressure is inversely proportional to the volume. As you reduce the volume, the pressure goes from P1 to P2. So it goes from P1 to P2 when it goes from V1 to V2. Now, when the volume is reduced, the pressure increases, and vice versa. So that's why its pressure is inversely proportional to the volume. So if you draw a graph of pressure and volume, what kind of a graph is expected? Pressure and volume?
As volume goes down, pressure goes up.
Yeah. So what's the shape? Inverse proportion. What's the shape of an inverse proportion graph? Yeah. That's the kind of graph that you can expect when you draw pressure versus volume, because now this, for example, here it is P1 and that is V1. According to this, it is the other way around. Over here it is P1 and the corresponding volume is V1. And over here it is V2 and P2. So as the volume is reduced, as the volume goes from V1 to V2, the pressure is changing from P1 to P2. That's an inverse proportion. Therefore, the product should be a constant. You can see from here to here also, the P times V is a constant. The product of pressure and volume should be constant. So that's Boyle's law. P1 times V1 should be equal to P2 times V2. That's how it goes. So when pressure goes up, the volume goes down, and vice versa, such that the product stays the same. Okay, that's the shape of the graph. Now, if you plot a graph of pressure and 1 over volume, like this, pressure proportional to 1 over volume, it's a straight line, right? Pressure is directly proportional to 1 over volume, therefore the line is expected to be straight. So that is your Boyle's law. Pressure times volume is a constant, but this relationship is true when all other things are kept constant. Whatever else can change. If you keep everything constant, then that is supposed to be the relationship. That's Boyle's law. Okay? And an easy way of checking it out is just a piston connected to a gauge, push it in, change the volume, get the new pressure, and you can investigate it very quickly. All you need is just this. Right? The next one. The Charles law. Charles law is it connecting or trying to get the relationship between volume and temperature, where you're keeping the pressure constant. So what is Charles' law's basic idea? The volume is directly proportional to temperature. Temperature absolute. When I write capital T, it's all capital T is absolute temperature. So volume is proportional directly to absolute temperature. And how do you understand that again? Volume is proportional to absolute temperature. Take the piston once again. And the cylinder. Cylinder and piston. Here we go. volume proportional directly to temperature. Temperature in Kelvin. Okay. And again, why we are talking in terms of Kelvin is because Kelvin is the thermodynamic scale of temperatures, where the temperatures are proportional to the average kinetic energy. Right? So if the average kinetic energy is 0, that means 0 Kelvin. So the average kinetic energy is what that one takes care of. That's why. Now, how do you investigate this? Let's say if I'm going to put this entire thing into a temperature bath, like temperature surrounding, a constant, some temperature. Now, if I just leave it like this here, if I leave it like that, the piston is left like that, what do you think is the pressure inside? There is some gas trapped inside, some gas. What is the pressure inside? Can anyone say it straight away? So whatever be it, what is the pressure inside here, straight away?
Pressure?
Yeah, what's pressure? Like this is the setup.
P1.
What is the pressure, the value?
Atmosphere.
Atmospheric pressure. That's atmospheric pressure. Why? Because outside is atmospheric pressure, right? And if the inside is not atmospheric pressure but higher, what will happen to the piston? It'll get pushed. It'll get pushed to that extent where the pressures are not held over there. The piston is not held over there. It is just like free. So if I ask you, all right, here's the piston. What is the pressure inside? Simply atmospheric pressure. Why? Because the piston is now in equilibrium, which means the force from here exerted by the atmospheric pressure should be the same as the force from here exerted by the inside pressure. So the inside pressure has to be the atmospheric pressure. So what is the pressure inside? Atmospheric. Right? Now what will happen? So when the pressure is atmospheric and when the temperature is T1, you can just measure this spot and that will tell you what is V1. Because the length of the cylinder tells you what is proportional to V1, right? This is just the length measurement, but then length times the area gives you the volume. So basically this is a measure of the volume. So if I measure the length from here to here, that is proportional to the volume. So we're talking about proportions. So if the volume is supposed to be proportional to temperature, this length is supposed to be proportional to temperature too, because the area is constant. You get it? Now, what will happen if I increase the temperature of this bath from T1 to T2? I increase the temperature. So what will happen is, these atoms are now going to be extra agitated, right? Because I've increased the temperature. So the average kinetic energy of these molecules have gone up. When the average kinetic energy goes up, what happens is they'll collide with a higher momentum. When they collide with the higher momentum, what will happen? Consequence? The pressure increases. When the pressure inside increases and the pressure outside is the same old atmospheric pressure, what will happen? This will get pushed. So when you increase the activity, when you increase the temperature, the absolute temperature of the bath, when you increase the temperature of the bath, the temperature of this is also getting affected. So what will happen is the atoms are going to go faster, and then they collide faster, they suffer more change of momentum, they experience more force, and they exert more force, and they exert more pressure. And when the pressure is more on this side, and the pressure is less on this side, the piston is not in equilibrium. So the piston starts moving until the pressure inside is brought back to. So we're keeping pressure constant in this. See, we are not doing anything. The pressure automatically becomes constant. We are only increasing the temperature, and automatically the pressure is held constant for us. And what do you see as a consequence? When you increase the temperature to T2, the volume changes from here to here. So the volume changes to V2. And what you can see is the volume that it is actually taking up is directly proportional to the absolute temperature. That's what you can see from here, from this experiment. You don't require a pressure gauge here. See, I didn't even attach a pressure gauge. All you need is a thermometer and a scale here. That's it. A thermometer and a small scale will verify Charles' law straight away. So if you are asked, design an experiment to verify Charles' law, here it is. That's a Charles law verification. What do you need? Just a piston. Trap some air inside a piston, leave it in this room. Check the length. Increase the temperature of the room. Come back. Length is different now. You understand what I'm saying? The length is different. Note the new length, note the new temperature, and you have this proportionality. If you plot a graph of volume and temperature, because this is a direct proportion, you're going to get a straight line. And this is in Kelvin. And why didn't I draw this part of it is because we are talking normal temperatures that we handle, which is like from 273 to 373. 273 is 0 degrees Celsius, and 373 is the boiling point of water. So we kind of deal with temperatures which are in this range. We never talk in terms of very low temperatures. So ideally, an ideal gas, which means a gas that obeys all the laws, will behave a straight line here. And what will be the expectation of an ideal gas? It's supposed to come to zero. It's supposed to come to zero. But most gases are real, and so they suffer other stuff. As you start cooling down, they change from, they liquefy and change into different things. So therefore, you cannot just continue that behavior all the way down to zero. So this extrapolation is just what is supposed to happen for an ideal gas. You get it? So that's supposed to be your absolute zero. Now, if you're going to plot a graph of volume versus temperature in degrees Celsius, not Kelvin. Now, degrees Celsius means this is zero. That's zero. So your experiment is going to move, be within 100 degrees Celsius. So basically, your experiment is going to be from here to here. That's it. So that's your experiment, and so you get a straight line. You will get a straight line. And if you extrapolate that graph, if you extend that graph, you're expected to touch here, which is negative 273 degrees Celsius. So that's a graph of volume and temperature, but the temperature is in Celsius. And we have negative 273, whatever, the absolute zero right there. We have this for sure, but these things are extrapolations, hoping that the behavior is going to be the same. And that's why we call it ideal gas laws. Ideal gas law, not real. What's an ideal gas? An ideal gas is a gas that behaves in such a way that it is obeying all the laws. It's like, who's an ideal student? You. An ideal student is a student who obeys every law, no violations. And the teacher teaches, you absorb 100%, not 90%. You absorb everything. An ideal student absorbs everything. And when the test comes, puts everything in, gets 100%. So who is an ideal student? Ideal student is one who gets 100% in everything. He plays any sport, he gets 100% on that. So if the ball comes to him, he's scoring it. Right? And there's no question about it. If the basketball comes to him, he's putting it in. No questions about it. 100%. Now, who is an ideal student? Nobody. Everyone is real. We're all real. I'm real. I make a lot of mistakes. So we are all real. And therefore, we change our characteristics under different situations. So that's exactly what happens here. This is what we know. I can understand. I can say that you're following the rules right now. Otherwise, you get jugged. You're following the rules right now. Your behavior is all according to rules and everything's fine. But I don't have any guarantee of what's going to happen outside this classroom. What you're going to do in your spring break or God knows. But right now, between the two bells, you are behaving as an ideal student. All right? And here is when changes take place to a gas. Everything can change. So this is a realistic behavior. Anyway, so that's why we call it ideal gas laws and ideal gas and so on. Okay. So what do you understand from here is volume is directly proportional to temperature. Again, keeping pressure constant, keeping other factors constant. And the other law is Gay-Lussac's law, or simply called pressure law. Yeah,
Negative that.
yeah. Pressure law. Pressure law simply says the pressure is directly proportional to the absolute temperature. Pressure depends on the absolute temperature. How do you investigate this? Simple again. You have a bath. You have a container that is sealed. And you have a pressure gauge attached to it. Since it is sealed, there's no change of volume. So volume is constant automatically, right? So you sealed it. There's no piston moving around. So therefore now the volume is kept constant automatically. Temperature is something that you can control. So what is happening in this container is that these atoms and molecules are moving, creating the pressure, and you can see the pressure is recorded by the instrument here. Now what happens when you increase the temperature? When you increase the temperature, the activity increases, they collide faster, but all of the factors are exactly the same, so eventually the pressure is going to go up. And the pressure is directly proportional to the absolute temperature. So again, the same thing. If you plot a graph of pressure in pascals or any unit versus temperature in Kelvin, you're expected to get a straight line. And if you plot the same graph, pressure versus temperature in degrees Celsius, same behavior again. Extrapolated to alright, so we have pressure law, which is pressure is proportional to the temperature when all else is kept constant. When everything is kept constant, pressure is proportional to temperature. So what are the different variables that you have seen just now? You've seen pressure, you've seen temperature, you've seen volume, right? So pressure is proportional to temperature here when volume is kept constant. Volume is proportional to temperature when pressure is kept constant. And pressure and volume are inversely proportional to each other when temperature is kept constant. But is there any other factor that is coming in? Is there any other factor that is coming in this? The amount. Like how many atoms are put in. The quantity of the gas that is trapped over here. That is a very important factor too. So pressure is proportional to temperature at a constant volume. But this pressure is not going to be the same, exact same value. It also depends on how many atoms are inside. How many atoms initially are you trapping inside? So therefore, the other factor that is going to come in is N, which is the number of moles. N is the number of moles. So we have all the factors that are coming in. So putting all these equations together, putting all these things together, so we have pressure inversely proportional to volume, you have pressure directly proportional to temperature, we have volume directly proportional to temperature, and we have pressure directly proportional to the number of moles, or you can also say volume is also dependent on the number of moles when all else are kept constant. So what you can see from here is pressure is proportional to volume times temperature oops, pressure times volume, because pressure times volume is a constant and is proportional to temperature, because volume is proportional to temperature and pressure is proportional to temperature, and it also depends on N. So PV is proportional to NT, where N is the number of moles, and the constant of proportionality is R. So that is what we call as the ideal gas equation, where R is called the molar gas constant. Capital R is called the molar gas constant. Pressure times volume. It's snowing. It's snowing in April.
This is
Gosh.
early discussion.
All right.
84 degrees 2 days ago.
Yeah, it's snow day tomorrow. All right. This year is very unusual, right?
Yeah.
Absolutely unusual.
Just being honest, it's not.
So, what is the unit for these two quantities? What is pressure times volume? What's the unit of pressure times volume? What's pressure's unit? Pascal is what? Newton per meter square. And what's the unit of volume? Meters cubed. So what is together? What is it? And what is Newton meter? Joule. So that is joule. Okay. So that is joule. This one is joule. This one is mole. This one is Kelvin. So you can figure out what is the unit of R. So the value of R is 8.31 joule per mole per Kelvin. That's a unit, that's a value, and that's a unit of R. Well, these are all in SI units. Yeah. In chemistry, you must have done
We did.
other numbers, right?
We did.
But they are not SI units, just for your information. They are okay. You can use those numbers, but you're not using SI units. What are the units? I think atmospheres, liters,
It's atmospheres.
Kilo.
liters.
something like that. Kilo atmospheres. I think there are some.
Atmosphere liters per mole. Kelvin, I think.
There it is. Yeah, liter atmosphere mole per mole Kelvin is one unit, and then calories per mole Kelvin is the other. And there are more numbers with that. So anyway, this is the only SI value. SI. You don't have to use anything else in physics. In physics, there's no other R, just one. 8.31 joule per mole per Kelvin. So if any calculation comes in, just throw that 8.31 straight away there, because P is measured in pascals, D is measured in meter cubes, not liters, N is measured in moles, T is measured in Kelvin. Okay. Now, how we use this equation, now, R is the molar gas constant. How we use this equation for problem solving is this way. If I keep the constant out, so you can see that pressure times volume over N times T is a constant, which is R. Right? So pressure times volume over N times T is supposed to be a constant no matter what. So if I have a container of gas, for example, I have a bottle. I have a closed bottle right here. Let's say in this temperature, I open the bottle and I close it. Just seal it. Okay? When I open the bottle and just seal it, what's the pressure inside? Atmospheric. And what's the temperature? Room temperature. So let's say the pressure is atmospheric pressure, which is 1.01 10 power 5 Pascal. And the temperature is room temperature, let's say it is 27 degrees Celsius. So if it is 27 degrees Celsius, now you don't require Celsius, you want in Kelvin, which is 300 Kelvin, right? If it is 27 degrees Celsius, it's 300 Kelvin. If I take this bottle from inside to the outside on a summer day, I take the same bottle from the inside to the outside and leave it outside on a summer day when the temperature is, let's say, 47. Pretty hot, like in Middle East. Now what is 47? 320 Kelvin. What is going to be this pressure? That's a question. So if I take the same bottle and leave it outside in that condition, what's going to be the new pressure? So what you do is come back to this equation. What we do is we write P1 V1 over N1 T1 is equal to P2 V2 over N1 N2 T2. That's how you compare any situation, anything. Now, what do you know about V1 and V2 in this scenario? They are the same because it's the same bottle, so knock it off. What do you know about N1 and N2? The same, so you can just knock it off. So in case there is a difference, if they say, all right, the same bottle is kept outside, but we pump in so many moles more, then that changes, right, under different situations. So this is a factor which normally doesn't come into problems, but it can be a factor also that comes in. And so what you have finally is P1. So all you do is substitution, 1.01 times 10 to the power of 5 over T1, which is 300, should be equals to P2 over 320. Remember, when you use this equation, when you compare P1 V1 over N1 T1, P1 can be in any unit. You can use atmospheres here and atmospheres here, that's fine. You can call pressures in any unit, but the same unit must be used here. Volume, you can use any unit, like you can use liters here and liters there, you know, can be anything. Gallons here and gallons there, that's fine. Number of moles, can be moles, can be number of atoms, but it should be same on both sides, doesn't matter. Temperature alone, seriously, must be kept in Kelvin. You cannot use any other unit of temperature. It should be only in Kelvin. So understand, when you're doing anything to do with gases, as soon as you see any unit, Celsius or Fahrenheit, that is not going to be acceptable for this equation. Change it to Kelvin immediately, and then work on it. So what's the pressure now? P2?
1.077 times 10.
That's going to be the pressure when you keep it outside. It looks like a tiny change in pressure, but that is a significant change in pressure. If I really do this, I've done this in the Middle East. Because in the Middle East you can expect that temperature easily outside. So an empty Pepsi bottle, an empty bottle of Pepsi, I just open it and close it. When I park the car in the morning, which is like almost that temperature, and then I leave it in the car, go to school. When I come back, it's so hot that I cannot enter the car immediately. At that temperature, you cannot enter the car immediately because it's like stuffy. So I can't touch the car with my hands because it burns. It really burns. 47 degrees Celsius, how many Fahrenheit? Convert it and see. 47 times 905 plus 32.
116.
116 Fahrenheit. Pretty hot. So you can't just get into the car and touch it. And in fact, the car inside the car can be still hotter. I've had burns with the seat belt. The metal part of the seat belt. I've got burns on that because you don't expect that kind of burn. So what I normally used to do is I go to the car, I open the door, I just start the car, put the AC on, close the car, just stand under the trees for some time, waiting for the AC to kick in a little bit at least. And once it kicks in a little bit, then I can just sit inside. But still it is. Most of the time, the car still stays hot till I reach home. It doesn't actually really cool. So it takes a long time for it to actually cool down because the whole thing is hot. So anyway, So this is something that I've seen, the Pepsi bottle, leave it inside in the morning. When I come and look at the bottle is like swollen. It actually swells. And you can see it like completely blown up. It doesn't explode, but it actually is blown up. And you can, all caused by a tiny pressure difference. So temperature changes will definitely cause pressure changes also. All right, so something that you can also see is this. Take a bottle from a refrigerator of water. Take a bottle, drink some water, close it, and you leave it outside. You took it from a cold place, but you left it outside. So what happens is the temperature, it gets warmer. What happens is the pressure goes up, significantly goes up, because your room temperature is different from the refrigerator temperature. And then the next time you say, all right, I want the water again, you open it, you can hear the hissing sound. As soon as you open, you can hear that hissing sound because the pressure inside is higher than the pressure outside. You get it? Now you must have heard that. When you open it, you can feel the air going in and out and all that. So how you use this equation is simply by this method. For any situation, you just blindly use this equation. And if there are changes in this, use it. If there are no changes, then use the other one. So what law is this? Pressure and temperature variations. What law is this? Being volume, the number of moles constant.
Pressure law.
The pressure law. Yeah, the Gay-Lussac's law. Going back to the kinetic theory, what was the last equation that we ended up writing down? Pressure is equal to 1/3 rho C bar square. So what is C bar? C bar is called RMS. C bar is the RMS speed square, and rho is the density and P is the pressure. And then if you look at it, pressure is equals to 1/3 mass of the gas and volume of the gas, C bar squared, and pressure is equals to 1/3 that's mass of the gas. Now, this is mass of the entire gas. So if you have the gas, this is M. The mass of each molecule is M. So this capital M is M times N. If you cross multiply, you get P times V is equals to 1/3 M N C bar squared. N is the number of atoms. Small n is the number of moles. What's the connection between small n and capital N? So, in other words, the number of atoms divided by the number of atoms in each mole is the number of moles. What is this called? Na. A stands for Avogadro's number. That's why I said this is the number of atoms divided by the number of atoms per mole. The number of atoms per mole is the Avogadro's number. So Na is 6.022 times 10 to the power of 23. This is the Avogadro's number. So the total number divided by the number per mole gives the number of moles. Right? It's like saying how many classrooms are here in school, at Trinity? Top of the mind, is the number of classrooms. I don't have the proper number, right? Now, do you know the total number of students in school, approximately? 1,400? Okay. The number of students per class on an average? 25, let's say? Okay? Sounds okay? No, on an average. What's the average class size? 25 or 20? 20, is it true? Okay. So number of students is 1,400. Number of students per class is 20. So how many classrooms are right now in operation in this school right now? 1,400 over 20. How much? 70 classrooms. That seems right. So you see how we can find the number of moles is by dividing the total number. Like in this room, how many atoms are there? That is this. Now, how many atoms per mole? That is this. So if you divide the total number of atoms in this room divided by the Avogadro's number, you get the number of moles in this room. You understand this? So n is n times, so n is n times Na. So I plug that here. You get PV is equal to 1/3 m n Na. What is this? What is that part of it? What is n? Number of? Oh, sorry, it's not that. Okay, this one. What is m times Na? M stands for the number of, no, the mass of each molecule. And this stands for the number of molecules per mole. So what is the product of these two? Molar mass. That's right. So PV is equal to 1/3 n molar mass I'll call it mm. That's a molar mass. So you can actually see the connections. The molar mass times the number of moles is supposed to give you the total mass. There it is. The molar mass times. So they're all interlinked. All these equations are interlinked. It's not that you have to come through the same steps. So you can see that number of moles times molar mass is the mass of the gas. Yes. Number of moles times mass of the gas. Number of moles times molar mass gives you the mass of the gas. And here it says mass of each molecule times number of molecules. That also is the mass of the gas. So it's all connected and it's interlinked. PV, according to ideal gas equation, it is nRT. And so nRT is 1/3 n mm c bar square. Cancelling off the n's on both sides. We have temperature R times T. R times T is equal to 3 mm c bar square. 1/3. Just testing you all. So what is c bar square? It will be 3 RT over mm. Right? C bar square is this. So what is C bar? Square root of 3 RT over mm. That's an important relationship. That's an important relationship where we are not talking in terms of pressure, we are talking in terms of these things. So you know R is 8.31. Temperature T is the temperature, absolute temperature. mm is the molar mass of the gas you're talking about. So what is the approximate? So if, for example, if I have in this room, I have hydrogen. There are hydrogen molecules, hydrogen atoms, right? Right in this room, there are hydrogen molecules moving about. Are there oxygen also? Yes? Yeah, oxygen is also moving around. Hydrogen is moving around, oxygen moving around, nitrogen, everything is moving around here in this room. Now, how fast, or what is the RMS speed of hydrogen? And what's the RMS speed of oxygen? Which one do you think is moving faster? Hydrogen or oxygen? In the same temperature, at the same room. hydrogen is moving faster. Why? The speed is inversely proportional to the molar mass. Hydrogen has less molar mass. Oxygen has more. And so, keeping all other factors constant, you can see that C bar is inversely proportional to square root of molar mass. C bar is inversely proportional to square root of molar mass. Because all these are constants. If I keep the temperature constant, all these are constants. And you can also see from here, for the same gas, C bar is proportional to that. For the same gas, which means these things kept constant, C bar is proportional to the square root of the absolute temperature. The root mean square speed is directly proportional to square root of the absolute temperature. The root mean square speed is inversely proportional to the 1 over square root of molar mass. Now the molar mass has to be proper units also. If you want to really calculate the C bar, you have to put the molar mass in kilograms. Molar mass should be in kilograms. R is 8.31, T is in Kelvin. Plug everything in, you should be getting the C bar. Or if you just want to compare the C bars, if you want to compare the RMS speeds, let's say go to this. What's the ratio of the speeds of hydrogen versus oxygen? So speed of hydrogen divided by the speed of oxygen. What is that ratio? Like how many times faster is hydrogen moving? All you do is, because it's inversely proportional to square root of molar mass, this is going to be that is proportional to 1 over square root of molar mass of hydrogen, and that is proportional to molar mass of oxygen. If I divide them, these get flipped, right? So it will be square root of molar mass of oxygen over molar mass of hydrogen. And you know the molar mass of oxygen is 32. And this one is 2. The molar mass is 32 and 2, and the ratio is 16. So what is square root of 16? And therefore what you understand is the C bar of hydrogen is 4 times the C bar of oxygen. So the hydrogen molecules over here, the root mean square of that hydrogen molecules 4 times faster than the oxygen slope. But they create the same pressure because they're going slower. Right? So they're going slower, but they're heavier, multiple factors come in. So the change of momentum depends on mass, velocity. Velocity is important, mass is important. So if you factor everything in, the pressure is going to be the same thing whether it is hydrogen or oxygen for the same temperatures. Hydrogen is H2, oxygen O2. Okay? And the other factor is temperature. Temperature. If the RMS speed is a certain value at a certain temperature, what happens is when the temperature increases, the RMS speed should go up, right? Let's say, for example, imagine the RMS speed of hydrogen in this room right now is 500 meters per second. Let's say, if it's hydrogen moving at 500 meters per second, and is proportional to the temperature in this room, let's say let's say 27 degrees Celsius. 27 degrees Celsius, which is 300 Kelvin. So 500 meters per second is proportional to 300 Kelvin. What should be the temperature so that the speed is doubled? If you want to double the speed, what should be the temperature? So if you want these same hydrogen molecules to go, instead of 500 but 1000, what should I raise the temperature of the room to? 1200 Kelvin, which is how many Celsius? How much? 927 Celsius. Yeah. So if I want to really make it go twice the speed, I have to push the temperature 4 times in terms of absolute in order to get this doubled. And so the temperature from 27 degrees Celsius should go to 927 if you want to really make this change happen, if it is going to be doubled. So speeds are going to change, but not too much, because the temperature change required will be enormous. All right, so you should be able to use this equation and compare them. All right. Average kinetic energy of molecules. The average kinetic energy of molecules. What's the average kinetic energy of molecules? If I ask you in this room, what's the average kinetic energy of molecules? What's the equation for kinetic energy? Half mass times which velocity? RMS. Because you know that they're not going at the same speed. You need the RMS speed for that. So half m RMS speed squared, that is going to be the kinetic energy. Now you go back and try to fetch an equation where you have some terms like that. So go back and where you had that one, see? mm n c bar square, is that what? Did you have that equation? No, n was not there, right? Yeah, 3 RT over mm, that's right. So you know this equation already. And what is mm? Molar mass. Molar mass is the mass of each molecule times Avogadro's number, c bar squared. So we need half mc squared, half mc squared. And here we have mc squared already. So what is mc squared? M times c squared is what? 3 RT over, right? I'm just leaving this mc square and throw the other things here. So 3 RT over, and what is therefore half mc squared is equal to 3 over 2 R over Na. So this is the average kinetic energy. Average kinetic energy is this, which is this. R is a constant, which is called the molar gas constant. Na is another constant called the Avogadro's constant. If you the ratio of these two should be a new constant. So the average kinetic energy is equal to 3 over 2 K. It's called KB. KBT. What is KB? KB is a new constant, which is called Boltzmann's constant. I don't know if there are 2 N's or 1 N. Let's see. Boltzmann's constant.
It's BALTACH.
No, it's not. That is yours. I'm trying to see if there are two ends or one end. Come on, where is it here? Yeah, that's right. Boltzmann's constant, Kb. Now, what is its value? It's R over Na. 8.31 divided by 6.022 10 power 23. Just do it yourself, you'll get it. This is in your data sheet anyway. It will be given to you. Kb is also given to you. Na is also given to you. R is also given to you. So there's no need to kind of memorize them or something like that. That's what it is. So what is average kinetic energy? It is 3 over 2 kT. 3 over 2 is a constant. Kb is a constant. T is the only variable. So what do you end up finally saying? Average kinetic energy is directly proportional to the absolute temperature. You get it? Isn't that the first thing I mentioned when we started talking about what's the difference between heat and temperature? Heat is the sum of all the potential and kinetic energy summed up. And what is temperature I defined as? We go back and see what I defined as the temperature. Temperature is proportional to the average kinetic energy. That's what it is. Temperature is proportional to the average kinetic energy. So when the average kinetic energy increases, your temperature increases. So what is the temperature at absolute zero?
Zero.
Yeah, what is the average kinetic energy?